Well, I mean, I'm going to wait for a few more people to arrive at least. Does anyone have any questions in the meanwhile? Oh, by the way, I should mention, while I wait for one more person, and I'll say this again, that the homework file that I sent out has a typo. I'll send it another one. And I sent that out just like 2 hours ago. So in Q, it was Q5B. X to the X, so this expression should be e to the X. That sounds more reasonable. And I'm really sorry for actually being so late on doing the homework. I mean, there was first an internet outage, and then just I couldn't motivate myself to actually verify all of the problems. And then I did it today because I needed to absolutely do it before today's lecture. Yes, the website will be up soon for some definition of soon. Okay, I guess we are going to get started then. So first off, any questions? Okay, so we are going to be talking about exact first order differential equations. And so we are going to have an equation of the form some function which will denote m for the first function. This is a function of x and y. This times dx plus n x comma y dy is equal to 0. And this is, of course, equivalent to the equation just n y prime plus m is equal to 0. But these aren't just functions of x, so it's not like a linear homogeneous equation, or it wouldn't be a homogeneous equation. But it's not linear because these aren't functions of x. So the claim that I made last time is we can consider the expression, for example, if k x y is some function. We define the total differential of k is by definition going to be something that we denote by dk. And this is going to be the partial derivative of k with respect to x, dx, plus the partial derivative of k with respect to y dy. And partial derivatives means differentiates with respect to x, treating y as constants. So I can give you an example of this. Let's say we have some function k of xy. And that's x cubed plus 3x squared y plus y to the fifth plus 5. So given this expression, let's find what's the partial derivative of x with respect to of k with respect to x's. And I'm going to introduce another notation for this. If I use a variable as a subscript, then it's going to denote taking a partial derivative with respect to that variable. And so I'm just going to imagine that y is a number. And if y is a number, then this is just a polynomial in terms of x. So if I differentiate that polynomial in terms of x, what polynomial do I get?
3x squared plus 6x y plus
yeah. And then this is just a constant with respect to x, right? So this is just 0. And then I may as well bring the y out front just to show you that it's a polynomial in terms of x, although that's not really necessary. And similarly, if I take the partial derivative of k with respect to y, which is also denoted by k sub y, what do I get?
uh, 3x squared plus 5y to the 4th.
Good. And thus, dk is going to be the expression 3x squared plus 6xy dx plus 3x squared plus 5y to the 4th dy. So partial differentiation isn't scary. The notation may look new if you haven't taken multivariable calculus. I'm not actually sure if multivariable calculus is a prerequisite for this course, but we definitely need this as part of the course material. But it's just differentiation. You just imagine that y is a number. Variables aren't scary. We're used to dealing with variables in our formulas, so it's not an issue. Well, okay, so what's the big claim? The main theorem is that the solutions to dk is equal to 0 are the curves cut out by the level lines of k. I'll say the levels of k. I'm not sure if that's the best thing, but I'll say exactly what I mean. What I mean is kxy equals c for c a constants. So we can imagine, like I said last time, that if we imagine graphing k in 3 dimensions, then we can consider sort of the value c here, and then we get a plane. This is z equals c. And then suppose that we have some kxy defines a surface. So at every point x and y, we get some heights. And the surface may look like well, it's sort of hard to say what the surface looks like from just representing it in 2 dimensions. But the point is that at some point, let's say the surface is going to intersect with this. And it's going to cut out a curve inside the plane z equals c. And the claim is that that solution is going to be a solution to the differential equation dk equals 0, where dk is the total differential and represents this expression. So in other words, if we have some differential equation of this form right here, and we are able to show that m and n come as the partial derivatives of some common function k, then we have a solution right away. And I should have extended this. Whoops, page 7. And I'm going to give like a sketch of why this is true. Because you shouldn't just like immediately believe me when I say this. We should justify it. And the sketch is, suppose that's the curve kxy equals c can be represented as a function of x. And what variable should I use? I used this before. So I'm going to introduce another Greek letter that's different from the one that I used in my notes. So suppose it's a function, or let's write it like this, x, and then let's call this function c, or psi, psi of x. So in other words, we are going to get y as a function of x, and it's going to sort of locally parameterize this curve. This isn't necessarily something that you can do globally, but you can do either one variable x in terms of y or y in terms of x, unless something very weird happens. But generically, you're able to do such a parameterization. So suppose c is psi is a function such that it satisfies this equation. So if psi is the function that satisfies this equation, then we can consider the expression d dx, because this is just a function of x now, of k of x, psi of x. And so if you have a function of 2 variables and you're trying to differentiate it, then there's actually a multivariable chain rule that applies. And we are going to use the multivariable chain rule. So what the multivariable chain rule says is that in order to differentiate this with respect to some internal variable, we're going to take the partial derivative of k with respect to x. I guess I'll write it in partial notation. And then we're going to multiply it by the derivative of x with respect to x. And then we're going to take the partial derivative of k with respect to y and multiply it with the derivative of c with respect to whatever variable we're taking the derivative internally of. So it would be with respect to x. So sort of this x and this x are unrelated, but that's what the result says. Now, what that gives us is this is just 1. So we get partial k partial x plus partial k partial y. And this is just the derivative of psi. And what is this equal to? This expression we assumed was equal to c. So this is equal to the derivative of a constant, right? And what's the derivative of a constant?
0.
Well, it's 0. Yeah. So basically what we get as a result then is that if we now replacing C with Y, we have that partial K partial X plus partial K partial Y dy dx is 0, and as a result, partial K partial X dx plus partial K partial Y dy is equal to 0. And so I showed that the level curves of this satisfy this exact differential equation, which means that if we have this differential equation, this shows that these are solutions under the assumption that I can make this parameterization, which isn't true everywhere, but that's why I called it a proof sketch. And the main ingredient here was that where does this step come from? Well, this is the multivariable chain rule. And I won't review that because it's sort of not relevant. The main takeaway from this is that if you have an exact differential equation, then it is the case that the curves kxy equals c are solutions to the differential equation. Okay, but the question is then, when is a differential equation exact? Well, the equation is this equals 0. And well, what can we do? So by definition, it is exact when what? What is the definition of exactness? So the definition is when there is a function k, so that dk is this. Which means that the partial derivative of k with respect to x is equal to n, and the partial derivative of k with respect to y is equal to m. But then what I'm going to do is I'm going to take the partial derivative of this equation with respect to y. So I'll get the second partial derivative of k, y with respect to y after x is going to be the partial derivative of n with respect to y. And similarly here, I'll get that the second partial of k with taking the derivative of x following taking the derivative of y is going to equal the partial derivative of m with respect to x. But there's another theorem in multivariable calculus that says that partial derivatives commute. So it's going to be generally true that assuming some basic niceness conditions, which we're going to have, so if m dx plus n dy is exact, then it follows that the partial derivative of n with respect to y is equal to the partial derivative of m with respect to x. And this is going to be an incredibly important equation that's going to dominate basically everything that we do in today's lecture. And so how do you remember this equation? Well, m is paired with x and n is paired with y. So you do the opposite thing. The thing that's paired with x, you differentiate it with y, and the thing that's paired with y, you differentiate it with x. If you remember that it's the opposite thing, then you'll get it straight. So the question is, if this is true, if this holds, then can we always find k? So that's the million-dollar question. And the answer is that yes, you can always find k, provided that the function is defined on a nice domain. So it's possible, for example, that m and n sometimes aren't defined, and there are holes in their definition. And when there are holes, sometimes it'll be impossible to define them globally. But let's assume that there aren't holes. Suppose that m and n are defined everywhere. On some rectangle A, B, C, D. And we will take all points to live in this rectangle. Now pick some point x naught, y naught. And we're just going to pick such a point, right? Then what I'm going to do is I'm going to consider the function, consider the function vxy is the integral from x naught to x of m with respect to s, keeping y fixed. So basically, y is going to be fixed, and then we're going to go from x naught to x. So what this looks like is that if this is our rectangle, and we've picked our point x naught, y naught, then in order to consider this quantity here, vxy, at some other point, which is, let's say, xy, we're going to ignore the y naught coordinates, and we're going to integrate m of y on here. So it's going to integrate m on this line right here. As x ranges from x naught to x, with y being fixed. So that's what we're doing. Now, why am I considering this function? Well, what I'm going to show is that, first off, if I take the partial derivative of v with respect to x, then what do I get by the fundamental theorem of calculus?
MSY.
So you're going to plug in x, so it's going to be mxy. Yeah. And the reason is that it's changing as the endpoint. So how quickly is it changing? It's changing by whatever this quantity is at the endpoint, right? Now, the thing is that we are looking for a function k, right? We are looking for k. If dk equals n dx plus mdy, then by definition, the partial derivative of k with respect to x is going to be m xy. Thus, the partial derivative of k minus v with respect to x is equal to 0. And what does that tell us? What that tells us is that k minus v is a function of y alone. Because at no point does it depend on x. Thus, if we consider k the function that we're trying to find, then it's equal to the integral from x naught to x of m s y ds plus some unknown function of y, right? So we've made some progress on trying to find k. Now, we know one more thing. We know also that k, the partial derivative of k with respect to y. Oh, raise hand, yeah.
Oh, y is the partial derivative of k with respect to x and xy.
Y is the partial derivative of k with respect to x. Yes. So we are trying to find a function k such that this is true. So we are going to suppose that we've solved the problem and that we have a function. Sorry, it's n. Thank you. So both of these, I've swapped the order here. This should be, say, I usually write m and n, right? So it's m, except I had the wrong thing written here. M goes first, right? I've written m first traditionally. Yes, m goes first. Thanks. So that was a typo. But assuming that it's dk, the total differential of k is this, then the following things are true, right? Good. Okay. So the partial of k with respect to y, well, that's equal to m now, but it's also equal to one more thing. It's going to be the partial derivative with respect to y of the integral from x naught to x of m s y ds plus, well, this is just a function of y. So if I take the partial derivative with respect to y, it's just the derivative. Right? Okay, now, so we have a derivative and an integral. This integral is with respect to sort of x-ish, and this derivative is with respect to y. What do you think we're going to do with the derivative and the integral?
Like chain rule?
So we're going to swap them. Because why not? So you can prove that this is something that's valid. Because this is sort of, there's x here and there's y here, and these are independent variables. And so you are actually allowed to do this. So it's not fundamental theorem of calculus. It's going to use a result about sort of limits commuting with each other, because this is defined as a limit and this is defined as a limit. And because things are nice in the general case, you'll get that you are actually allowed to change this order. Now, here's the key step. Look at this quantity. So this is going to be, let me just actually rewrite this. There, that looks a bit nicer. So what was our hypothesis? Our hypothesis is that the equation that we have for exactness holds, right? So if I have the quantity I think I made a consistent mistake in that I replaced n and m here, where I started with m and n, and I replaced it with n and m. So I'm just going to correct that right now. I'm going to replace all instances of m with n, just to remove the confusion. So this is actually m and this is actually n. So the partial of m with respect to y is the partial of n with respect to x. In this equation, m dx is n dy. Okay, so given that I didn't accidentally do the swap. So what we wrote here was correct, except we changed what n and m meant. And that was an issue because we're using a different meaning elsewhere. But if we have this equation, then what happens is we have the partial of m with respect to y here, right? And so we can replace that with the partial of n with respect to x. And now, since y is just going to be fixed, we can treat y as a constant, and we can treat this as a derivative with respect to x of this expression, treating y as constant, right? And now the fundamental theorem of calculus applies. So we're going to, what is this quantity going to equal? So remember that the integral of f prime of x dx is from a to b is equal to f of b minus f of a, right? So if we treat y as a constant and just treat this as a derivative with taking the derivative with x, then what we get is the expression n of x y minus n of x naught y, right? And the partial derivative of k with respect to y, I made the mistake again. This is actually n. The second one, right? So what we have is that n of xy is equal to n of xy minus n of x naught y plus phi prime of y. So it follows that phi prime of y is n of x naught y. Therefore, it follows that phi is given by, now this x naught is just a constant, so it's given by integrating n of x naught comma y dx. And since we actually want to put a concrete number on this, let's say we're going to integrate from y naught to y. Y is the upper bound. And just to make this clearer, this isn't with respect to x. Let's keep the variable t here and dt. And then, since we've sort of fixed y, at this point, a constant comes in. Although we're actually not going to care about that constant. So what happens then is that we found phi, and we now know what k is. Therefore, it follows that k of xy is going to be, let's see what we have first. First, we have the integral of m from x naught to x, the integral of m of s y ds plus the integral from y naught to x of n x naught t dt. And so if you actually think about how to interpret this, let's imagine that we have a rectangle again. And let's imagine that we have the point x naught, y naught, and the point xy. So this argument on n, as we increase on y, it uses x naught. So you can sort of imagine taking this point here, which is x naught y, and then what you're doing is you're integrating n here. And then you're going to integrate m here. Now, this formula, why not do it in the other direction? Why not integrate here first and there first? Well, that's actually what exactness is. Exactness is precisely the property that if you integrate from here to here along any path, then it doesn't matter what path you take, you'll always get the same value along that integral. And that's what enables you to solve this problem. So basically, if we took any path whatsoever, even if it's sort of swirled around itself, and we integrated a certain expression that came from this windy path, we'd get exactly the same value as if we did this combination of integrals because of exactness. And exactness came very crucially into this calculation in this step, which is what let us evaluate this integral. So basically, that's the abstract argument as to why the condition for exactness, that is, if you take the function on x and you differentiate it with y, and you take the function on y and you differentiate it with x, if those partials are equal, then you should be able to solve for what k is. And if you're able to solve for what k is, then you know the solutions are kxy equals c. Any questions about that? We're going to do concrete examples in like a second. So I will make one remark. If m and n fail to be defined somewhere, then it may not be possible to solve for k globally. But it will exist locally. So the thing is that at every point you can find a small enough rectangle so that it's defined everywhere, right? So in that rectangle, you can solve for it. But the problem is that basically if there's a hole, then you might not be able to define it everywhere. So the failure, I will just say something from graduate math classes. This is going to be a term. The failure of closed forms. And these are things satisfying the equation. So closed forms are anything that satisfies the equation m of y equals n of x. So if this equation holds, then the form is called closed. The failure of closed forms to be exact, which means m dx plus n dy is equal to dk. So this is measured in mathematics by something called cohomology. And if you go on to study graduates topology courses, you'll know that cohomology is one way to talk about the shape of things. So for example, a cohomology can tell you how many holes there are of where your function is not defined. And so this is studied in graduate topology courses. Specifically algebraic topology courses. And I know a lot about this. And then the statement that a solution locally exists is basically the statements that like domains in Rn are locally nice. They don't locally have a shape. Okay, so, or I mean, their shape is not interesting. So that is just a term. Cohomology basically measures how many holes there are via failure of this equation to be satisfied. And it's a really cool thing in algebraic topology that you could basically study when this equation fails to hold, when this holds, and that actually tells you about the shape of the domain that you're considering. Okay, so that was a total interlude. Let's get on to some examples. So let's consider, for example, the equation. And by the way, this is how you're going to solve these problems from now on. So let's consider the equation e to the x cos 2y dx plus 9y squared minus 2e to the x sine 2y. Is equal to 0. Okay, so when you're writing your solution, I don't like M and M to be just conventions. You should actually label this as M, and you should label this as N. So I do want these labels to exist in your solution. Or you can write M is equal to this and N is equal to this if you're typesetting it on a computer. Okay, so if you have that, then let's consider M partial y, right? So M is the thing associated with X, so you take the Y partial of it. You do the opposite, you flip them. So if we're taking the partial derivative of this with respect to Y, what do we get?
Minus 2e to the x sine 2y.
Good, exactly. And then if we're taking the partial derivative of N with respect to X, what do we get here?
Minus 2 sine 2y e to the x.
Yeah, because the only thing that depends on X is this, everything else is a constant, so this goes away and the derivative of e to the X is e to the X. And in particular, these expressions are equal. Okay, so once we've determined that it's exact, and I cannot emphasize this enough, you 100% certainly have to check that an equation is exact before you do anything. I'll show you how wrong things go if you do not check that it's exact. So now, since it's exact, what we know is that we're going to take some facts from the above exposition, and we're going to say that K is equal to the integral of M S y ds Or rather, since I'm taking the indefinite integral, I want this in terms of x. I'm going to take the indefinite integral. Treating y as constants and treating this as a variable, x. Plus some function of y, right? We are going to remove the bounds and we're going to make it an indefinite integral. But otherwise, this is what our previous exposition told us, because definite bounds are only going to change this by a constant. So what happens then is we can actually integrate this expression. So if we take this expression and we integrate it with respect to x, treating this as a constant. So when we do these integrals, y is going to be constant. It's not a function of x. And because we're trying to find some function k that works, not all functions k that work, because the constant comes in later, where you're not going to care about constants. So if I integrate, well, cos 2y is constant. If I just integrate e to the x, I get e to the x, right? Now, what is phi? Well, I know that n is equal to the partial derivative of k with respect to y by definition, right? And what is the partial derivative of k with respect to y? Well, I have this quantity right here, and I'm going to differentiate it with respect to y, keeping x as constant. So the derivative of cosine is minus sine. So I get minus 2 e to the x sine 2y. And then I take the derivative of this with respect to y, and I get phi prime of y. And then if I look at what n is this expression here, 9y squared minus 2e to the x sine 2y. So what does that tell me about the derivative of phi?
It's got to be 9y squared.
Good. And we don't care about constants. We just want to find some antiderivative. So phi of y is equal to
3y cubed.
good. And that tells us that k is going to be this expression to here, e to the x cos 2y. Plus phi of y, which is 3y squared. And that tells us that the solutions, and this is where the constants comes in. So we didn't care about constants because we just wanted to find some k, and then it's going to be the level curves of k. So kxy equals c. In particular, the actual solution is this. So this is what you write down as your final solution. And so this is how you solve exact differential equations. So the process to review, and we're going to do it a few more times today, is that we know from the previous exposition that k can be given as the integral of m plus some unknown function of y, and with respect to x. So we treat y as a constant, we do this integral, and then we get that k is this plus this. Well, we know something about the partial derivative of k with respect to y. So we partially differentiate this with respect to y. We get some expression, and then we compare it to n. And that tells us what phi prime is. Then we integrate phi prime, which should be a function of y. If it's not a function of y, something has gone very wrong. And then you get you solve for phi as a function of y by doing another integral, and then you get k, and then you know what the solutions to the differential equation are, right?
I just have one question.
Okay, now I'm going to do another example. And this is an example of why it's very important to check for exactness. So for example, consider the differential equation. Yes, here it is. Cos x cos y. Dx plus sine x sine y. So let's not check for exactness. We forget to check for exactness. And so what we say then is that if this is m and this is n, then for dk equals m dx plus n dy, we have k xy, or I don't have to write xy. K is equal to the integral of m x y dx plus some function phi of y. So this is the formula that we go to at the start for all of these exact integral calculations. So this is just we're treating y as constants, and when we try and integrate cosine, what do we get?
It's just cos y sine x.
Yeah, exactly. I will put the sign first because the x went before the y. Sure. Sine x cos y. Okay, cool. So then partial of k with respect to y is going to be the part, this is plus phi of y. So partial k with respect to y, the derivative of cosine is minus sine. So we get minus sine x sine y plus phi prime of y. And what is this equal to? This is equal to n. So what does that tell us? That tells us that phi prime of y, where phi is a function of y alone, is equal to 2 sine x. And this literally does not make sense because what is x? So phi is not a function of y alone. And at this point, this is a mathematically nonsense equation. I guess my x doesn't really look like an x, but here now it looks more like an x. Because you can just change x to be any different values, and then like this isn't even a well-defined quantity, right? So at this point, the solution would become slightly nonsense if you try to integrate it with respect to x. And so this went horribly wrong, and this solution path does not work. And even if you treated x as just a constant and integrated this, you would not get the right solutions to the equation. So, oh, and there's a question in chat. 3y cubed. Way back when I integrated Yes, somehow the cube turned into a square. Thanks. Good. It's important to have it corrected in the notes for when I send those out and when you study from them. Okay. And now we've done an hour. So let's break for 15 minutes and resume at, actually it's 56. Let's imagine that it's 55 and resume at 7:10. Okay, see you then. Okay. Right. Okay, now let's talk about integrating factors. In a more general sense than we talked about last time. So what we talked about last time is actually going to be a special case of this more general notion of integrating factors. So remember that the meaning of m dx equals n, sorry, plus n dy is that it defines the direction fields at every point of the plane. And that's given by the slope of a line. So it's given by the ratio. And this is given by slope. So I guess we'd say solve for dy dx. So it would be m over n, except for the fact that we're bringing one of these over to the other side. So negative m over n, right? And this can be infinity if n is equal to 0, for example. Well, the thing about this is that this quantity, it doesn't change if we multiply m and n by some fixed function of x and y. If mu of x, y is any function, then mu m dx plus mu n dy equals 0 defines the same direction fields. Now, obviously, there are some super silly things that you can do. So for example, you can take mu equals 0, and then that doesn't define a direction field at all, right? So if you do something like multiply by 0, that, okay, you've lost all the information. But assuming that you multiply by something that's invertible at least almost everywhere, then you're going to get the same direction field at least almost everywhere. So the point is basically that this equation might not be exact, but by multiplying it by a certain mu, it becomes exact. So if this equation, which I'll label as 1, if 1 is exact, then mu is called an integrating factor. And so in general, we're going to solve problems by first checking for exactness. And then when we see that it's not exact, we're going to find an integrating factor. So the theorem is that integrating factors always exist, assuming some niceness. Or rather, instead of writing assuming basic niceness, if m dx plus n dy, I can make this very precise, equals 0 has a solution, then it has an integrating factor. Moreover, it has a solution in all nice cases. But there's a huge caveat, buts. This solution or integrating factor do not have to have nice expressions, or it's not necessarily possible to write it down in terms of elementary functions. Might not be expressible. So the situation that we have with differential equations is basically universal for all classes of problems. In general, assuming that the solution isn't, assuming that the equation isn't absolutely terrible, and if it has a formula, then it's basically guaranteed to not be absolutely terrible. There are theorems that guarantee the existence of a solution, but those solutions might be only theoretical. It might be impossible to write down the solution in a nice way. And in this course, we're really only focusing on situations in which there exist nice expressions. Unless, I guess, until the end of the course, I might talk about numerical methods, and then we're going to see how to numerically get these solutions. But anyway, so that's an interlude. The point is that the method of getting an integrating factor is a pretty general way for solving this equation. So when we have an equation like this, unless it's one of the previous classes of problems that we discussed, because this is a general first order equation, right? For special cases, we just spent the last 6 hours of the course discussing special cases, right? So if it's a linear differential equation, then you apply those methods. If it's like a Bernoulli equation, then you apply those methods. Or if it's a homogeneous equation, then you apply those methods. But if it's not any of those, then you're going to try and find an integrating factor. So basically the algorithm for first order ODEs is ask if it's separable. Check, is it separable? If it is, then you're done, right? Because we know how to solve separable equations. 2, is it linear? 3, so a more general version of linear equations is Bernoulli. 4, we also spoke about homogeneous equations. And then if no to all, check if it's exact. Then what you do is check if it's exact. And if it is, then you're done. And if it's not exact, then find an integrating factor. And I'm about to explain how to do that. So actually, what we're going to talk about in integrating factors is going to be the last thing that we do for first order equations. We are going to subsequently be studying second order and higher order equations and systems of equations. So in other words, now that we actually have our full toolbox, I can give you this general algorithm. And you should 100% remember every single trick in here, right? Because this course is about learning tricks and then learning how to apply them. And so here are all of the tricks. And just to remind you as to what these are, separable equations are equations of the form y prime is equal to f of x g of y. Linear equations are equations of the form y prime plus f, which is a function of x, y, equals g x, another function of x. Bernoulli equations are equations of the form y prime plus f x y is equal to g of x y to the n. And homogeneous equations are y prime is equal to some function that's a function of the ratio x over y, right? And then maybe there might be some problems in which you reduce an equation to an equation of a different form. Although I'm not sure if that's going to come up. And to remind you, exact differential equations are equations m dx plus n dy equals 0 with my equals nx. Okay, so here is your master table for first order linear differential equations. So know everything here. Where we're going to discuss how to find integrating factors right now. So that's going to be that. But that's your algorithm. So you literally just do all of these whenever you encounter a first order problem. I mean, you don't have to check if it's one of these if you immediately know that it's another thing. So like if you see that it's a Bernoulli equation, you don't have to like separately check, is it separable? Is it linear? If you see that it's a Bernoulli equation, you see that it's a Bernoulli equation. Okay, sure. Any questions about this? Okay, let's move on. So what about integrating factors? Well, if mu m dx plus mu n dy is exact, then what do we know? We know that the partial derivative of mu m with respect to y is equal to the partial derivative of mu n with respect to x. And now we are going to use chain rule. So this is going to, it follows therefore that the partial derivative of mu with respect to y times m plus mu times the partial derivative of m with respect to y is equal to the partial derivative of mu with respect to x plus mu times the partial derivative of n, times n with respect to x. And then we can rearrange this equation to obtain that I want to write it like this. M d mu dy minus n del mu del x is equal to, and then we can factor out a mu here. And notice that in this equation, the partial derivatives, yeah, they're the swap derivatives. Okay, so let's look at this expression right here. So if this expression is 0, then what does that tell us?
Before you, it was already exact.
Yeah, so if it's, this is exactly the condition for exactness, right? So basically what we can do is now we can rearrange this equation. What we're going to get then is that, well, okay, before we rearrange this equation, what is this anyway? This is a partial differential equation. because it involves partial derivatives. So it's not an ordinary differential equation. And in general, solutions to this are outside of the scope of this course. So unfortunately, I'm not just going to give you a formula for being able to find the integrating factor in all cases. However, there are nice cases. And these cases are actually all of a certain form. They're going to be cases in which the integrating factor has a special form. So basically, they're going to be ansatz on what the integrating factor are. We will assume ansatz on the form of mu. And we're going to consider several cases. Case 1 is going to be that mu is just a function of x. Case 2 is going to be that mu is just a function of y. And case 3 is going to be that mu is a function of the product of x with y. And then we're not going to do it here. Maybe I can assign one homework problem in which I asked you to work this out. But you can also consider mu as a function of x over y, or mu as a function of y over x. You get slightly different formulas for these, despite the fact that sort of they're the same. Maybe I won't write the other one. So you know what? I think I'm going to add a question to the homework in which I asked you to work out this case in the way that I'll work out those cases. So I'm going to modify the homework. I'm going to add one problem to the homework. And then I'm going to resend that. And then there's also a typo in the homework for people who weren't here at the beginning. So I sent the homework out today. I'm really sorry. I promised to send it out on Friday. It's due in a week from now. But when I sent it out, there was a typo. In question 5b, I wrote x to the x, whereas it should actually be e to the x. That's sort of more reasonable. This is sort of, I mean, if you want to know what x to the x is, then it's by definition e to the log x times x, right? That's what the definition of that is. But I don't mean that. I actually meant e to the x, right? Okay, so let's consider case 1.
I was gonna say no worries. Are you sending out the new homework problems tonight?
You know what? Okay, I'm going to promise that I'll do so. So I'm just going to add one question to the homework, and I'm going to fix that typo. And unless I find any more typos.
And then
However, I'm going
sorry.
to guarantee that there won't be mistakes in the homework to the best of my ability by writing out solutions. And I think that I'll write out solutions in the next 2 days. At least I'll try and do that. And that'll sort of guarantee that there aren't any typos that I miss. Like I did a bit of
Cool.
test solving before setting this assignments. I can't set an assignment without doing test solving. That would be terrible. The problems would not work. But I'm going to do like a complete comprehensive test solving in the next 2 days where I actually typeset solutions for this. And then I can tell you that there aren't typos in it only after that point with like very high certainty.
Yeah, that sounds good. Are they still going to be due on the Monday, a week from today?
They are.
Okay,
By the way,
sounds good.
so basically you can start working on the problems. If you're able to solve a problem, that means there isn't a typo in it. And there should be, there won't be more than one typo that I haven't caught.
Sounds good. Thank you.
Did you send the homework on Blackboard or did you send it to our emails?
I sent it on Blackboard, so you're not on Blackboard yet. I'll
Yeah,
forward
I
that to you.
still don't have. Okay, thank you.
By the way, just sent it out earlier today, so
Okay.
you haven't like missed anything.
Okay.
Like you're not a few hours, you're only a few hours behind on not receiving it.
Okay, thank you.
Okay, so case one is integrating factors that are functions of x alone, right? So let's go to the equation for an integrating factor, which is this equation right here. And you know what? I'm actually, this is the equation. And by the way, I should mention that the homework, I think that this assignment is actually easier than I would have wanted it to be. And the reason is that I definitely had to have it ready by the start of today's lecture. And if I spent a few more hours working on it, I would have been able to come up with more tricky problems. But I had to come up with problems that I was pretty sure were good, and that I couldn't risk putting more tricky problems because they'd be more experimental. So because sort of that time constraints, and I said that I do it on Friday, but I only did it today. I will strive to actually have some like more clever problems on subsequent assignments, but you know what, it's fine. Let's just keep the homework as it is. I'm going to add this one problem here, which is, I guess, a bit more interesting about considering this case. But otherwise, the problems just go through every single type of differential equation that we've considered. And I don't label the problems with what type it is, but it goes along the progression of the material. So you can sort of use that as a meta reason to just figure out, oh, so we're currently on this section that's treating homogeneous equations, for example. Okay, so let's go to this equation for an integrating factor. I guess I can zoom out for a second, or I can copy it over again. I'll just copy it over again. So I'll write out what the equation is. So it's m mu partial y minus n mu partial x is equal to mu n partial x minus m partial y. Okay, now let's imagine that mu is a function of x alone. So on SOTS, mu xy equals mu x. So it's just a function of x. So what's the partial derivative of with respect to y of a function that does not depend on y? It's just 0. So we get, as a consequence, that minus n mu x is equal to mu. And when I write mu x, I actually mean mu prime, because it's just a single variable function. So when am I able to solve for this? Well, I can rearrange this as d mu over mu, right, is equal to nx minus my divided by negative n dx. Now, this side right here, this is a function of x alone, right? But in general, there's no guarantee that this will be a function of x alone. So if it isn't, then this equation does not make sense and our odd sorts is useless. So if nx minus my divided by negative n does not equal to f of x, a function of x alone, then our ansatz is useless. Was bad. Right? However, let's suppose that it is. So suppose that this is a function of x alone. Then what do we know? Then if we integrate this with respect to mu, if we integrate this, what do we get on the left-hand side? Or rather, I should ask another question first. If this is a function of x alone, then what kind of differential equation is this? You're muted. I think you're trying to speak, but you're muted.
Then it's like, oh.
I
It's,
can hear you now.
oh, wait.
So this is just mu, and then this is a function of x. So there's d mu here and there's dx here. So it's
Separable.
yes. And not only is it separable, but it's already separated, right? So then integrating the left-hand side, what do we get?
Log of mu.
Yeah. And then on the right-hand side, we just have the function x. So that's the integral of f of x dx. And we only care about finding some integrating factor because the constant is going to come in later, so we don't care about the constant. And so what we get is that, remember that if we're trying to solve for like exact representations of equations or for integrating factors, we only care about finding one of those because the constant comes in later. Okay, anyway, so here we get mu is equal to the integral of e to the f of x dx. Okay, so then we're able to solve for the integrating factor. So what's the general recipe then? We are going, by looking at this quantity, we're already checking if the differential equation is exact or not, right? Because if the differential equation is exact, then this is 0 and we're done. And so we don't have to care about it. So in any case, you're going to have to compute nx and my in order to know if the differential equation is exact and whether you even have to find an integrating factor. But once you've computed them, then you just take their difference and then you try and divide it by n. And if when you divide it by negative n, you get a function of x alone, then we know how to find the integrating factor. So that's the step. You look at this difference, you divide it by negative n, and you see, is that a function of x alone? And as a mnemonic, n is associated with x in the differential equation. So when you divide by n, you care for it to be a function of x. So here's an example. Sorry, n, it's the opposite of what I said. N is associated with y. So when you divide by the thing with y, you get a function of x. So it's the opposites. So the opposite of the mnemonic that I just tried to say. N is associated with y. And so it's a general theme that it's opposite things. The differential equation for exactness is opposites, and this is also opposites. So let's consider the differential equation y plus 3 y squared e to the 2x dx plus 1 plus 2y e to the 2x dy is equal to 0. And so what we have here is I would like you to label your solution to define this as m and to define this as n. So we're on the same page about what m and n mean. Okay, so the first thing that we do is we check for exactness. We need to compute the partial derivatives. So we do the opposite thing. So m, the thing on x, gets the y derivative. And what's that?
One plus 6e to the 2x times y.
Yeah, good. Okay, and then we take n, and we take the opposite derivative of it. So we take the x derivative, and what do we get?
For y e to the 2x.
Good. Cool. Now, remember that the equation that we're considering is the second one minus the first one, right? So first off, it's not exact. We can see that it's not exact. So we're not done. If it were exact, well, I mean, we wouldn't be done. We'd still need to do stuff. However, if we consider nx minus my, then what we get is 1 plus 2y e to the 2x. And look at that. That's exactly the expression that we have right here. But except for the fact that remember that there's a minus sign here. So nx minus my divided by negative n is going to equal to not 1, but negative 1. And then we go back to our equation for an integrating factor. And the way that you should write that equation is like this. So therefore, d mu over mu is equal to -1. I would like you to write it like this in your assignment. Don't remember the formula, remember this equation. That's that function of f is what d mu over mu is. Well, rather it's not -1. That sort of doesn't make sense. It's -1 dx. That's the way you should write it. That actually makes sense. So we get that log of mu, and remember, we don't care about constants because we just want something, is -x. Sorry, I made a mistake here. N minus m is actually, it's actually going to be negative this, right? So actually it's going to be +1, not -1. Sorry about that. Okay, so as a consequence, we've solved for our integrating factor. Our integrating factor is e to the x, right? Now, what does that mean? That means if we go back to our original equation and we multiply by e to the x, we get an exact equation, and we know how to solve those. And then you should write what you get. So what you get is, well, I have it written down. It's y e to the x plus 3y squared e to the 3x dx plus e to the x plus 2y e to the 3x dy. And sort of this is provably exact. We don't have to check if it's exact because if we did the previous step correctly, then it will be exact by the method that we showed before. So if you look at the original equation, you can see that, well, we got an e to the x here, the 2 became a 3. We got an e to the x here, the 2 became a 3. So yeah, I multiplied it by e to the x correctly, which is exact. And we're not going to check for this. Okay, so what we can do with this is now that we can solve an exact differential equation. So if this is dk, or I guess if the left-hand side, then we know that k is equal to the integral of the first expression with respect to x, treating y as a constant, plus some unknown function of y alone. And so, okay, so y is constants. E to the x becomes e to the x, and then we have 3 e to the 3x. Well, the 3 goes away. Okay, now we take the partial derivative of k with respect to y. And we're going to first compute it from this expression. So that's e to the x plus 2y e to the 3x plus phi prime of y. And what's that equal to? Well, you should remember that the equation that we're considering is this equation, not the original equation. And so what that's equal to is e to the x plus 2y e to the 3x. And so what that actually implies is that phi prime of y is equal to what?
0.
Yeah, and so in particular, integrating 0, one particular integral of 0 is 0. So actually, I have 3 examples that I've prepared for how to find integrating factors. And by complete accident, in all 3 examples, I get that phi prime y is 0. This does not generally occur, by the way. I've shown you an example, the first example that we did of an exact differential equation. We actually had that phi of y, phi prime was not 0, and we actually had to integrate it. But as it happens, I am about to do 3 examples in which by pure coincidence, we keep getting that this is 0. But if it's 0, then we can conclude something. We can conclude that k is just, well, this is 0, so it's just y e to the x plus y squared e to the 3x. And what does that tell us about the solution? So what are the solutions?
When that equals to C.
Exactly. The level curves of this expression. And then I can box that in. And that's my solution. Okay, let's do the case that's completely analogous to this one. This was the case in which we had that it was a function of x alone. Let's do the very similar case in which it's a function of y alone. So mu of y. Well, let's go back to our equation for an exact differential equation. It was m mu y minus n mu x is equal to mu nx minus my. Now, if mu is a function of y alone, then the mu derivative with x vanishes. So what we get is that m mu prime now just is equal to mu, which is a function of y alone, nx minus my. And so what we get now is we don't get the minus sign. Now we get the plus sign. We get that d mu over mu is equal to nx minus my. So it's still the second one minus the first one. But now we divide by m dx. So this is a function of Well, if we're just treating mu as a function of y, well, okay, this is with respect to mu. And then this expression right here, it only makes sense if it's with respect to x. So our ansatz is only good. So basically what we did is we had the ansatz. That's mu xy equals mu y. So ansatz is only good if this is a function of, wait, let's see, did I do it right? Sorry, this is d mu dy. This is with respect to y. So the ansatz is only good if nx minus my divided by m is equal to, let's say, some function f of y, right? So if that's the case, then we do what we did before. What we have is that log mu is equal to the integral of f of x dx, and so mu is equal to e to the integral f of, sorry, f of y dy. This is a function of y. Okay, the exact same thing that we had last time, except for the fact that we're now dividing by m instead of negative n, and we want it to be a function of y. But the point is that you're still computing this difference and then trying to divide it by one of the things. So here's an example. So I'm going to consider yeah, I just looked at my notes for a full half page of notes. Okay, I am here. Negative y sine x plus y cubed cos x dx plus 3 cos x plus 5y squared sine x dx, sorry, dy is equal to 0. Let me just check that. Good. Okay, so the first thing that we do is we check for exactness. And I'd again like to label the equation with this as m and with this as n, so that I know what m and n mean in the first place. And then we compute the part y partial of m. And okay, well, it's just a polynomial. So we get minus sine x plus 3y squared cos x. And then the n partial with respect to x is, well, what's the derivative of cosine?
Minus.
Yeah. And then here, okay, and then so the derivative of sine has to be cosine. Yeah. Okay, so this is not exact because these two things are not the same. However, if we consider the second one minus the first one, which is the same thing that we consider in the first example as well, what we get is, so this minus this, we get minus 4 sine x. Sorry, this becomes a plus, so it's minus 2. And then 5 minus 3 is 2. Now let's compare it to this expression. So sine x, y squared cosine x, except there's a power of y here and there's a power y1, y3. Here there's y0 and y2. However, this looks promising because this does look like a multiple of that. So I can also rewrite this as, well, okay, I'll just say nx minus my divided by m, positive m in this case, is so minus 2 sine x plus y squared cos x divided by, and then I can factor a y out of this. There's no, I actually do want the minus sign here. Let's keep the minus sign here. Better. So I can factor a y out of this. And so what I get, and just checking that I got it right, is 2 over y, right? Thus, we solve d mu over mu is equal to 2 over y dy. That is not a y. And so we get log mu is what?
2 log y.
And when I exponentiate that, what do I get?
Y squared.
Good. So that's my integrating factor. Thus, multiplying the original equation by y squared gets, okay, and then it's this thing right here, but I'll just write down, I have it on paper as to what you get. You get minus y cubed sine x plus y to the 5th cos x dx plus 3y squared cos x plus 5y to the 4th sine x dx is equal to 0, which is exact. It will be if we did our previous technique correctly. And so now we're solving an exact equation. For I was going to write for dk, and so I wrote k core. For left-hand side is equal to dk. Have k is equal to the integral of m with respect to x. Plus some function of y alone. And okay. What's the integral of minus sign?
Cos.
Good. And so here it's the opposite thing. There was a minus, yeah, that's what happens. Sorry, that's the sign. And now we compute as to what k partial y is. Okay, well,
Is
this is
it
just
plus sign?
Sorry?
Is it plus sign? Y 5th plus.
The integral of cosine, yes, is positive sign, correct? So the sign doesn't flip. The sign only flips on one of them. Thanks. Good catch. Yeah. So we get 3y squared cos x plus 5y to the fourth sin x plus phi prime of y. And what's that equal to? That's equal to n of in this expression, which is 3y squared cos x plus 5y to the fourth sine x. Oh, look, we get that same case, which is going to happen with the last example that I do as well. And this is completely coincidental. I swear this doesn't usually happen. Okay, so then our k equation is what we had before with that as 0. Which tells us that our solutions are that equals c. Okay, let's see how I am for time. It's 8:01. Okay, yeah, so let's take a 9-minute break until 8:10, and then I will do 2 more things. Any questions about this so far? Okay, yeah, I was planning to do these 2 examples before the next break, and then I prepared exactly the right amount of material for today. Okay, let's do the third case. And the third case is when mu is a function of the product of x and y. So we go back to our equation for an integrating factor, which is m mu y minus n mu x is equal to mu n x minus my. And now what we're going to do is we're going to say ansatz mu x y is in fact mu of the product of x and y. Okay, what happens then is we're basically going to do chain rule. So if we take the partial derivative of this with respect to y, then what do we get?
Well, so like partial derivative of m respect to y, and then times mu y, and then
Well,
and
so
then
x is a constant. So you're doing chain rule here. Imagine that y were a number. Let's say we had just had mu is equal to, x were a number, 2y, and we took the derivative of this with respect to y. Then what would we get?
derivative the partial derivative of d mu dy times
Yeah,
yeah.
mu
Uh,
prime of 2y times what?
U prime times 2.
Yeah. And so if instead of 2 we have x here, then instead of 2 we have x, right? Because x is just a constant. So what we're going to get is x times m, mu prime of xy is minus, and then when we do here, we're going to get the same thing-ish, except for the now fact that we get y out front. So mu is a single variable function, except we're going to evaluate it at xy. And so as a result, we get mu xy and x minus my. And so as a consequence, when we take d mu over mu, which is evaluated at xy, this is going to equal to the expression as sort of, I guess, let's say we're going to make a substitution z equals xy. Then we'd get, then this would be d mu dz. And so what we get is nx minus my. Something happened to my throat. Divided by xm minus yn. And so the ansatz, well, rather dz, where z is equal to xy. And so this is useful if this is a function of xy.
Wait, is that nx minus mu y?
as the numerator.
mx minus yn nx nxmy.
Okay.
Sorry, is it's something that I wrote unclear letter-wise? That's
No,
an
just
M,
like
not
the
an U.
coefficient.
I
Okay.
think that might be the problem.
Yeah,
Was that the
that's what I was
problem?
wondering. Yeah.
Yeah, okay, fix. If and only if this is a function of z equals xy. Okay, so let's do an example. So basically, this is a weird case where you have to divide by this expression and see if it's a function of x and y. So let's consider the example 3y cos x plus y minus xy sine x plus y dx plus 3x cos. And so I've looked at a few examples of this form, and they all seem to have this sort of symmetry. So if it looks like there's some interchanging of x and y going on, then you can sort of begin to suspect that it's going to be something of this form. But basically, when you're finding an integrating factor, and none of the previous types of things worked, you basically first try and divide by negative n, then you try and divide by m. And then if that fails, you consider this expression. And those are the cases that I'm really going to test. Okay, so we have that this is m and that this is n. And first we check for exactness. So my is equal to, well, okay, so we're going to get a chain rule expansion here. So it's going to be 3 cos x plus y. And then when I differentiate this, well, it's just the derivative of cosine is negative sine. That's only the first term, but then we have to do the second term. So then we get minus x sine x plus y. But we're not done yet. We also need to differentiate the derivative of sine is cosine. Okay. And nx is, well, basically we're interchanging some x's for y's. So and then minus 3x sine x plus y. And here, again, we're now taking the y partial derivative. So the x partial derivative. So now the y survives. And I'm just writing this out quickly because there's a big symmetry in just swapping x and y in these equations. And then minus xy cosine x plus y. Okay, notice that these terms agree, but these terms do not agree. There is a 3y here, there's a 3x here, there's a y, and there's an x. However, also, yeah, we can't combine these. I mean, we can put a sine x plus y out front. So basically, we can rewrite these as well. This is also equal to, okay, 3 minus xy cos xy x plus y. And then for this minus 3y plus x. sine x plus y. That's not a super elegant way to write it, but whatever. And here we get 3 minus xy cos x plus y. But the second term is going to be different. Now it's going to be minus 3x plus y. And so that's different. So we can conclude from this that this is not exact. However, if we take nx minus my, so the second thing minus the first thing, we always consider that expression when it's not exact. Well, these two terms cancel out. And so basically what we get is minus 3x minus y plus 3y plus x sine x plus y, which is equal to 2y minus x sine x plus y. Okay. Now, if we sort of divided it by this big expression, if we divided it by m or n, it's not nice, right? Because we get a cosine and a sine here, but we only get a sine here. So that's not nice. So what we instead do is we consider xm times minus ym. And so if we see what we get, then if we multiply this by x, we get 3xy. And if we multiply this by y, we get 3yx. So these terms are going to cancel out, right? So what's left over? X times m is x squared, y sine xy. And here we have x y squared. So we're going to get minus x squared y plus xy squared, right? Times sine x plus y. That's what we get left over. So how did I get that? Well, I noticed that if I multiply this by x and I multiply this by y, then these two terms cancel. And these two terms are pretty similar. I mean, they're the same. So we just get this term x squared, and here we get y squared. And so it's minus x squared y plus, because I'm subtracting x, yn, plus xy squared, which is exactly what I have here. But then I can factor out an xy out of this, which is good because I like having functions of x and y. That's what I want. And then I get a minus x plus y, or in other words, a y minus x, which is what I have here. Sine x plus y. Oh, so that's good. So then nx minus my divided by xm minus yn is going to be 2y minus x sine x plus y divided by xy, y minus x sine x plus y. And that's equal to 2 divided by xy, which is a function of, which is equal to, let's say, f of xy for f is equal to, let's say f of z is equal to 2 over z, right? Then consider d mu over mu, that's our integrating factor equation, is equal to f of z dz is equal to 2 over z dz. Okay, so we got logarithms. So as a consequence, we get that the logarithm of mu is 2 times the logarithm of z. And so I've already asked this a few times. We get mu is equal to z squared. So that's our integrating factor, which is equal to, because we don't want it in terms of z, we want it in terms of xy. So what is z equal to?
XY.
Yeah, so x squared, y squared. So our integrating factor is x squared, y squared. Then multiplying. So notice that in order to have this make sense and this be a sensible integral, we had to abstract x, y into z. And then we had to carry through the calculation in terms of z, and then we had to plug it back in. So that's what's going to happen when you have examples of this form. Then multiplying the original equation by x squared, y squared, you get the following equation. And let me make it a bit brighter in here. Let's see. By the way, this writing application that I'm using, I think it's like the perfect writing application. And what do I want in a writing application? Well, first off, it has to have a night mode. And it has to, you should be able to set custom colors. And then the most important thing is that I don't want it to just be a bunch of pages. I would like the height of the pages to increase. And like, so Microsoft has, oh, my headphones are, earbuds are dead. Let's see. So Microsoft has like OneNote or something, and it has none of these features. And it's like, okay, a company like Microsoft is releasing this. They only have a fixed number of colors. You can't set custom colors. It does not have a night mode on OS X. It has a night mode on the most recent Windows version, but not on OS X. And you can't set the page heights to be arbitrary. So like, what's okay, so this application, by the way, is called Write by Stylus Labs, in case you're curious. And you can also do whiteboarding. So like with my advisor, we connect here and then we write together on the same board. So it's cool. Anyway, going back to here. So we take this equation, we multiply it by x squared, y squared, and get the equation 3x squared y cubed cos x plus y. Minus x cubed y cubed sine x plus y dx plus 3x cubed y squared cosine x plus y. And then minus x cubed y cubed sine x plus y dy equals 0, which is exact. Thus, for left-hand side is equal to dk, we get, and then we do our usual process. So k is going to be the integral of m with respect to x. And so when we look at this, we're actually going to be a bit clever now. So instead of integrating this directly, what we're going to observe is that there's a cosine here and there's a minus sign here. And there's a 3x squared here and an x cubed here. So this looks like a product rule thing, right? And so what product does that come from? Remember that y is just a constant.
Wait, what do you mean?
So I mean, we can try and integrate it directly, but look, there's a 3x squared here, and then there's an x cubed here. And the derivative of x cubed is 3x squared, right? And then there's a cosine here, and then there's a minus sign here. So it looks like this comes from a product rule application. And so you ask yourself, what products do I differentiate to get that expression? And the answer is,
X cubed sine x plus. Oh,
so we keep the y cubed there. And then is it sine or cosine?
Cosine.
Yeah. Why? Because here we differentiated the 3x, we differentiated x cubed to get 3x squared. And so this is undifferentiated. Whereas on this side, we did not differentiate x cubed, but we differentiated cosine to get minus sign. Okay, so this was just like, if you tried to do this integral separately with both of these integrals, you would not necessarily have fun. But we observed that just looking at this begs to be on product rules. I guess if you did integration by parts, probably that would probably be the way to go if you wanted to do this directly. And then just to be helpful to the reader, you note by product rule. That's sort of a helpful remark as to how you actually got that. So it's not out of thin air. It's sort of really suggestive of that. Okay, so now we take k with respect to y. And so that's going to be 3x cubed y squared cos x plus y, and then we do chain rule. So then we get, sorry, product rule, x cubed. Oh, but we're differentiating cosine, so we get a minus sign. Plus phi prime of y. And remember what I said before, by complete accident, the three examples that we're doing today, so the equation is this. And by the way, a common mistake that you can make is go back to the wrong equation. It's the exact equation that we're solving. And so that's what n is. And so we get as a consequence that phi prime is 0, and so phi is 0, and so k is just this expression. And so the solutions are x cubed y cubed cos x plus y equals c. And that's the problem. So what you do is once you looked at this equation and you determined that you were going to do it via trying to do this exact method, you test if it's exact, you try and divide by n, you try and divide by negative m, or rather you try and divide by first by negative n and then m. And neither of those would work. And so, okay, at this point, you consider this expression, which is highly unintuitive. It's only if you know about this method that you'd actually consider this. And then you try and see if that's a function of x, y, and it is in this case, so it's good. And so on the homework, I'm going to get you to consider the case mu is equal to x divided, it's a function of x divided by y. But I'm not actually going to have that come up on exams. So it's just going to be one problem for working it out and then also trying it on an example. So I did it 3 times, you're going to do it a 4th time here. Okay, and so that actually ends the section on first order equations. So basically what we spent the first 3 classes, so the first 5th of the course on the first order equations theory. So let's celebrate that. And so this is what the content of the first assignment is. The first assignment is entirely on first order equations. I want some blue in here as well. So now we are going to very quickly, in the remaining time, introduce a tiny bit of second order theory. So in general, a second order ODE is an equation of the form so we're going to have some function that's going to involve x, it's going to involve y, it's going to involve y prime, it's going to involve y prime prime. And so if you have some equation involving x, y in its first two derivatives, then that's called a second order ODE. And it's an ODE and not a PDE because we don't have partial derivatives. Okay, but in general, like with first order equations, so there isn't an as nice interpretation of these equations as there was with first order equations where we had direction fields. Now sort of the second derivative is involved and we can picture that less exactly. So that's a bit unsatisfying. But we can consider a few special cases of this. So a second order ODE is linear. Linear second order ODE has the form. So it's going to be y prime prime plus some function f that's only a function of x times y prime plus g, a function of x times y, and then we're going to get some function hx. And so this equation is going to be known as homogeneous when what?
H of x equals here.
Exactly. Okay, so a general second linear second order ODE is an equation of this form, and it's homogeneous when this happens. And so in general, as we discussed before, the solution space to the homogeneous equation is going to be a vector space. It's actually going to be a two-dimensional vector space. So there are going to be two constants, and then you're going to have two equations which you can multiscale and add, and then you're going to get that space. But then when you have an inhomogeneous equation, there's going to be a particular solution to the inhomogeneous equation, and the general solution is going to be that particular solution plus any multiples of the two generating functions for the solution to the homogeneous equation. So we're going to, I said that very quickly, but we're going to go over that in a lot more detail tomorrow. Now, a special case of this is when f and g are constants, when they're just numbers. And in general, a general second order linear ODE with constant coefficients has the form. And in general, we might have like a number on the leading term we could divide through and not have it there, but then we have fractions. So it's sort of better to allow for a number to be on the first thing. So it's going to be a y prime prime plus b y prime plus c y is equal to, and then let's still use h of x. For a comma b comma c numbers. So they're just regular numbers. Okay, well, sure. So now what I'm going to do today is I'm going to consider the homogeneous equation. So let's solve the homogeneous equation. And that will be ay prime prime plus by prime plus cy is equal to 0. Okay, and we are going to solve this by way of an ansatz. And the ansatz is going to be that y is equal to e to the tx for t some number. So let's see what happens when we use this ansatz. So when we use this ansatz, what we get is that a, and now if I take the derivative of this with respect to x twice, what do I get?
T squared e to the t.
Exactly. So by chain rule, each time I take the derivative of tx, I get a multiple of t. And so here I'll just get b t e to the tx. And here I'll just get c e to the tx is equal to 0. And all of these, they're multiplied by tx. So what we get then is we can factor tx out, and we get at squared plus bt plus c e to the tx is equal to 0. So what do we see as a result? Thus, t is a solution of the quadratic. At squared plus bt plus c is equal to 0. And actually, okay, that reaches the end of my notes. Actually, you know what? I prefer, oh, go ahead. You were raising your hand?
Oh, because I was thinking that like the it looks a little like for the spring equation, but then you wrote y equals e to the tx. So then I would guess maybe it's like the solution to the quadratic is imaginary, and that's how you get like your signs.
Yes, exactly. So let's you know what? Let's review one more thing today. Sure. I'm going to do exactly one more thing today. So first off, let's review how we solve quadratic equations. Okay, come on. Oh no, oh no, please don't crash. Okay, it did not crash. If it crashed, then I would have lost a bunch of notes, and that would have been bad. So let's quadratic equation review. So, okay, if we have this equation, the solutions are, okay, sing the song. There is a song.
Minus b plus or minus square root b squared minus 4ac over 2a.
Yes, that's the song. It sort of fits into a song. Okay, so that's the quadratic equation. Okay, so for example, if you have x squared plus 2x plus 1, well, first off, if you have something like this, you would never in your life use the quadratic formula for that, because you can immediately factor this as x squared plus, x plus 1 squared. Similarly, if you have x squared minus 1, then that's difference of squares factorization, right? Now, what happens if you have something like x squared plus 1? Well, so first off, if you take any number and you square it, you get a positive number, or a non-negative number to be more exact. And then if you add a non-negative number to 1, then you get, you can't get 0. So that's a bit of a problem. But let's just look at this expression and let's see what the quadratic formula says. So according to the quadratic formula, what would the solutions be? Well, b is 0, So it will be plus or minus the square root of minus 4 times 1 times 1 divided by 2. And certainly, okay, let's just ignore the negative sign. The square root of 4 is 2. So this becomes plus or minus the square root of -1. And so what we're going to do is we're going to introduce complex numbers. The square root of -1 is going to be known as the imaginary unit I. And the equation that I satisfies is that I squared is equal to -1. So I is going to be a square root of -1. Now you ask which square root of -1, there are technically 2 of them. So by convention, we are going to assume something like this. And so complex numbers have the form, are numbers of the form so x plus I, y, for x and y real numbers. Okay, let's just review some basic properties about complex numbers. I should have given myself more space. So I don't have to, I don't like it when I have to like expand by touching at the bottom. So I have to make sure. Okay, so let's imagine that you have, let's say, a plus ib times c plus ib. And so if you were going to expand this out, then you would never use the acronym FOIL. It's sort of telling of the American education system that they have an acronym for expanding something like this. Anyway, you multiply a by this, so you get a c plus a times id, and then you get ib times c, and then you get plus I squared b times d. So now let's rearrange this. What is I squared equal to?
-1.
Yes, so we can write this as AC minus BD. And then we can group these terms with I in common. And so we get AB, which is sort of the cross terms, plus BC times I, right? So basically, the product of the real with the real minus the complex product of the imaginary with the imaginary times I times the cross terms. So that's how you multiply complex numbers, right? And now, out of complete thin air, I'm going to assert that we have Euler's formula. Which is the statement that e to the I theta for theta, a real number, is equal to cosine theta plus I sine theta. So this is, okay, so this is when theta is a real number. So then, for example, exponentials are going to behave with the usual properties and how they behave with real numbers. So for example, if I take e to the alpha plus I beta, then that's going to equal e to the alpha times e to the I beta, right? So assuming that exponentials take sums to products, as they usually do. And so that would be e to the alpha times cos beta plus I sine beta. I don't know, maybe it's better to write the I at the end. So basically what happens then is that if you think about the expression cosine theta plus I sine theta, let's imagine that we're going to plot this on the complex plane. So we have a complex plane, This is sort of the real axis, and that's the imaginary axis. And this is the imaginary axis. So real numbers live here, purely imaginary numbers that have no real part live here, and they intersect at 0. And then all other numbers are here. So if I considered a point whose sort of real coordinate was cosine of something and whose imaginary coordinate was sine of something, what would the collection of all such points look like?
A circle.
Exactly. Because by definition, what is cosine and sine? What are the definitions of cosine and sine? Basically, if you take a unit circle, let's say this is the unit circle. What is the circumference of a unit circle? I didn't hear that. 2 pi. Yes. Okay. I hope that it's not me that's lagging. Someone is lagging. It might be me. Okay. Sorry if it is me that is lagging. So the point is, what are radians? Radians are a measure of arc length. So basically what we do is we start here. And we go in this direction. In mathematics, the positive direction is counterclockwise. And so we measure a distance of theta along here. And that's the same as the angle theta in radians. And then if you have the angle theta in radians, the key point is that this coordinates is going to be defined as, by definition, what is the definition of this point at where the line of theta intersects the unit circle?
Cos theta plus I sine theta.
Comma sine theta. Yeah, so that's the definition of the cosine and sine functions. You take the unit circle, you measure arc length to get an angle in radians, and then you shoot this ray, and then it intersects the circle at some point, and the coordinates of that intersection are exactly cosine theta and sine theta. So if you have a number like this, that represents a thing on the unit circle, and then the e to the alpha represents a magnitude. So the e to the alpha changes the unit circle to some general form. So in general, what we have is that if z is a complex number, and the complex numbers are written as c, then z can be represented as r times e to the I theta, where theta is defined up to 2 pi, right? Because cosine and sine theta are defined up to 2 pi. So this is called the polar representation of a complex number. And so if r is 0, then theta isn't defined at all. And if r is non-zero, then theta is defined to an additive factor of 2 pi. Okay, so what else can I say about complex numbers? So we're going to use complex numbers a bunch. And so you sort of can also look at this equation that we had right here, and you can imagine that this is x squared minus I squared, and then it's difference of squares. Then the solutions are x minus I and x plus I. Okay, so let's go back to this equation right here. Let's imagine that we had the equation x squared plus, rather lambda squared plus 1 is equal to 0. So this corresponds to the differential equation of y prime prime plus y is equal to 0, right? And so the solutions are e to the it and e to the minus it. And so what happens here then is that in general, when you get complex roots, they're going to be of the form a plus I plus or minus ib, because that's what the quadratic formula gives you. So it's going to be some real number plus or minus something, some I times some other number. And so those are known as conjugate pairs. That is assuming that the differential equation started off with real coefficients, right? So let's assume that our that our quadratic started off with real coefficients. Then if it has complex solutions, those complex solutions come in a conjugate pair. So if lambda, let's say a lambda squared plus b lambda plus c is equal to 0. And then when is this going to have complex solutions? It's going to have complex solutions when what is less than 0? There's a name for it.
Delta?
Sure.
Sorry, you say that again?
Was it delta? The triangle, right?
Okay, I guess in some places they call it delta, but I like to call it the discriminants. And so what the discriminant is, it's the expression b squared minus 4ac is less than 0, because if it's less than 0, then the quadratic equation has, you're going to be taking the square root of a negative number. In this case, the solutions are so well, they're of the form are going to be let's say let's call it maybe alpha plus I beta and alpha minus I beta. And this is known as a conjugate pair. And the reason that we get a conjugate pair is because we started off with real coefficients. So if we look at the quadratic equation, then specifically we can say that alpha is equal to x equals negative b divided by 2a. And then beta is going to be, well, we're taking the square root of this negative number. So beta is going to be the square roots of 4ac to make it a positive number, minus b squared divided by 2a, right? And then we get an I here, which is accounted for here. So complex roots of real polynomials come in conjugate pairs, which is actually really interesting because then we're going to get something cool happening. Because then the solutions in general we discussed can be linear combinations of these solutions, right? So let's go back to our original equation. In y prime prime plus y is equal to 0, got that the solutions were c e to the it, because it's a linear equation, you can scale and add solutions, plus let's call the next constant d e to the minus it. And so an equation like this is a solution. So y equals is a solution. However, let's use Euler's equation on this. We get c e to the, so this is going to be it is cos, so cos t plus sine t plus I sine t. And then this is going to be plus d cosine of minus t plus I sine of minus t. And now there's a symmetry between cosine and sine when you negate it. So one of these is an even function and one of these is an odd function. And so to remind you, cosine, sine is locally linear, and cosine looks like this. If you take cosine of minus t, what is that equal to?
Cosine of t.
Yeah, so we get c cos t. Let's actually group these together. So you get c plus d cosine of t. And then here we get plus I times c, and then minus sine of minus t is the same as negative sine of t because sine is an odd function. So c minus d sine t. And so here's the catch. If you consider the equation c plus d is equal to alpha and c minus d equals beta, this can always be solved, right? So if you want c plus dt equals something and c minus dt equals something, then you can always solve for that, right? So in general, you can replace these coefficients with the coefficients alpha cosine of t plus beta times I sine of t. And actually, the thing is that beta can be any complex number. So let's look for real solutions. If we want real solutions, then beta is going to be purely imaginary. And then we can basically consider actually the equation I c plus b equals beta and solve this in imaginary numbers. And then if we are looking at real solutions, the real solutions are exactly of this form. So the real solutions are actually written in terms of cosine and sine. And so next class, I'm going to review that again, and we're just over time. So we got a bunch of things about complex numbers in. And so if we're finding real solutions, then we're not actually going to go for the imaginary roots. We're going to turn this conjugate pair into cosines and sines. And then we're going to consider real coefficients, and then we're actually going to enter the world of real solutions to those differential equations, which is what we want. But as an intermissionary, we're going to solve the polynomial over the complex numbers. Okay, so there's a typo on the homework, and I'm going to correct that. And I'm also going to add one more problem to the homework, and I should send that to you soon. Are there any questions before we wrap up for today? Okay, so if you, this is how you do the homework. The homework is on first order ODEs. And if you remember, we considered separable, linear, Bernoulli, homogeneous. And then if no to all of those forms, then what we're going to do is check if it's exact. And if it's not exact, we're going to find an integrating factor, right? So that's your algorithm. So I'm going to send you these notes and keep this algorithm in mind because this is how you do the homework. Okay, have a nice day, and I'll see you on Wednesday. Bye. Oh, and there is one thing in chat. Okay, yeah.